Okay, last time we have talked about uh, for fixed sample size, there is a trade-off between your type 1 error alpha and type 2 error beta. That is, if you want to reduce a type 1 error, you may need to sacrifice a type 2 error. If you want to reduce a type 2 error, you may need to sacrifice a type 1 error. So for a fixed sample size n, you can't reduce the type 1 error and type 2 error at the same time. There is also another thing that I would like to talk about regarding the role of the sample size n. Recall that we mentioned in the video when we talked about power. When we increase sample size n, the standard error will decrease, and that will increase the value of test statistic. When the value of test statistic gets bigger, then your p-value will get smaller. And the rule of thumb is when p-value is less than alpha, then we reject h-norm. So your p-value is smaller, which makes the p-value less than alpha more easy to happen. That will increase your power. So if you're having more subjects in a study, that will make you find statistical significant results more easily. But you are having the statistically significant result may just because you have a big sample size. So the statistical significance is not practical significance. Having a statistical significant result does not necessarily mean that the result itself is practical significance. You really have to look at the context of your practical question. So small p value does not indicate results will have meaningful impact. On the other hand, if your results are statistically significant, if your results are not statistically significant, that doesn't mean your results are meaningless as well. This is actually many times true when you are in the psychological field. For example, you are trying to see whether a new way to help depression works or not. You may not have a statistical significant result, but that doesn't mean the new way of treating depression is not worth exploring, because humans are kind of complicated. Not statistically significant result does not necessarily mean it's meaningless, and very likely that you may just not have enough power to detect the effect. So let's take a look at this following example. If you haven't read the example yet, you could stop the video for a moment and work on this example and by yourself. So in this example, we try to conduct conduct the hypothesis test of whether the Wake County make more income than the state average versus this mu equals to the state average 59481 versus the alternative hypothesis mu greater than 59841. So the first step, establish a null hypothesis and alternative hypothesis has been provided in the question. The second step is to check on conditions. So this is a large random sample. So the conditions met. Then the next step, let's calculate the test statistic. This is the formula to calculate the test statistic. And if we plug in the numbers we got from the question, this is our sample mean minus the mu now divided by sample standard deviation over square root of sample size 100. So this is our test statistic. The now distribution is a t-distribution with degrees of freedom equals m minus 1, which is 99. So the p-value will be calculated under h now in the direction of HA. So we have talked about how we should find the p-value. That would be under the null distribution when the t-distribution greater or equal to your test statistic. What is the probability that you will find a test statistic that is more extreme than the observed test statistic? And if we use StatCrunch, we will find this is 0.179. So this is a pretty big number. If we most of the time, if alpha is not given, we assume our alpha is 0.05. So suppose alpha is 0.05, our p-value is less than, is greater than the alpha. So we can't reject H now. So this is an example, and we can see that based on the sample we collected, we reject H now. If we use the same data to conduct another test, now the only thing that's different is suppose we are collecting a sample of sample size 5,000 instead of n equals 100. Then all the other things will be the same. Your test statistic will be like this. Square root of 5,000. So this is 6.52. Then the now distribution right now is a t distribution with degrees of freedom equals 4999. So the p-value is calculated under h now in the direction of HA. HA is mu greater than 59481. So the p-value you are trying to calculate will be probability t greater or equal to the test statistic you calculated. This is basically a 0. This is obviously less than the alpha, so we reject H now. Now you can see it's the same question. We want to see whether the families in Wake County make more income than the state average or not. The answer should be either we reject H now or we can't reject H now. The true answer will only be one of them. But you are having the same hypothesis, same sample statistic, but just because you have different sample size, this is 5,000 here and this is 100 here, you are having a completely opposite conclusion. So you can know, like I said, you don't know which one is right, which one is wrong. You know, this is like I've mentioned in the hypothesis test, either you make a mistake or we didn't. We really don't know for sure which one is correct, which one is wrong. So again, what I want to emphasize is if you have a statistical significant result, that doesn't really imply that it is practical significant. Conversely, if your results are not statistically significant, that doesn't necessarily mean the result is meaningless. You shouldn't explore more on it.